And so we'll just have to draw on our experience with polynomials in high school, so. Okay. So yeah, so I wanted to state, I realized that I hadn't stated theorem 3.6, and a lot of you were using it on the homework, which is fine. I mean, it was in the textbook. But I realized we had never stated it in class. So I wanted to go ahead and state theorem 3.6 because it is like an even shorter shortcut to showing something is subring. So it's kind of nice. Maybe more useful than 3.2 because it's just 2 steps instead of 4. So okay, so this only has 2 things. We have S is closed under subtraction. So what does that mean? i.e., for all A, B in our set S, A minus B is in S. And the second thing is S is closed under multiplication. And so that means for all A, B, and S, A, B. Get a better marker. Okay, and so how does this compare with theorem 3.2? Remember what theorem 3.2 had you do? So for theorem 3.2, I'm just going to write them side by side. It starts out the same way. Oh, I didn't write the conclusion. Then S is a subring. So this one had 4 things. So one is S is closed under addition. The second thing is S is closed under multiplication. The third thing is what? Do you remember? 0 is in there. Yeah. So 0. Does it need to be 0S or 0R?
0R is in S.
Well, is that always true? Because like that subset that we had of Z mod 10. Remember this subset of Z mod 10? It's a is it a subring? It's a subring. Right? It's a ring in and of itself, right? And a subset that is a ring. It doesn't contain 1, but it has an element that acts like 1, right? 6 was the element that acted like 1. Remember that? So,
but it's 0, right?
It needs to have a 0 in there. So what does the theorem say?
It says 0 sub r in this. That's what I have in my notes.
0 sub r, isn't it?
I mean, with that, stuff that you still have zero so far in that. It's zero.
Oh, 0. Yeah, sorry, that was me being dumb. 0, but it could have a different multiplicative identity. Right, okay, sorry. I just kind of went nuts for just a minute there. Sorry. Yes, no, 0. So it has 0. Oh gosh, okay. Okay, so yes, so it has to have a 0, the only 0 element. So the 0 element in a subring is the same as the 0 element in a ring all the time. Okay. Sorry. Thank you for clearing that up in my brain. Okay. So it's not even a Monday. I can't even blame it on that. Okay, and what's the last one that has to be the theorem 32? The additive inverses. So for all A and S, negative A is an S. So it's additive inverse has to be in there. I think it was stated in terms of equation solving in the. Yeah, so I think it's, so this is the way I think of it in my brain. But I think you could say A plus X equals 0R has a solution. This is equivalent. Yeah. So. Okay, so why are these the same thing? Well, the closed under multiplication thing obviously translates directly, right? But the subtraction bit should get us the other things, right? And how does that work? Can we prove it? Okay, so we get the closed under multiplication bit. So, so what we want to show is that these properties satisfy these properties, which we've already shown satisfy the ring properties, right? So, so since S is closed under multiplication, it satisfies condition 2 of theorem 3.2. Okay, so we've got that one. Okay, that was the easy one, right? Now, why might the rest of these things be true? So we're assuming that it's closed under subtraction and multiplication, right? Okay, so let's say assume that S is closed under subtraction. What can we say? Good, yeah, so since A is an element of S, we can do A minus A needs to be an element of S, right? Yeah, so I think it's stated here A minus B, but this is for any A, B, and S, so we could take B to be A, and we'll have A minus A gives us the 0 element. Does that make sense? Okay. So since S is non-empty, there exists an A and S, and A minus A is an S by the first condition. So A minus A equals 0R is an S. Okay. So we got that one. So that's condition 3 of theorem.
And it gives us 4, isn't it?
Why?
Or not 4. Or yeah, 4 because what we're saying is the A plus X. Where you're adding a negative X.
How does it give us 4? Now what elements do we have in our ring? We have A and 0R. So we can apply this closed under subtraction thing. Right? And what do we want to subtract? So I know that A is an S. I also know that 0R is an S. So that means that what is an S? Why?
Because S is something to add,
Well, it's because what? Because you can take any two elements of my set and subtract them. Right? In what order do I want to subtract them to make a negative A show up?
0 or minus A.
0R minus A, right? Because it's closed under subtraction. I know 0R is in there. So 0R minus A is in there, but 0R minus A is equal to negative A. Yeah. Okay. Since 0R is in S, by that first condition, we have that 0R minus A is in S. But 0R minus A is equal to negative A, so negative A is in S. So for any element, I picked an arbitrary element in S, and I found that it's additive inverses in S. Right? So I got that. Okay, can I show that it's closed under addition? Why? Yeah, so to show that it's closed under addition, I need to take two elements of S, right? So I'm going to start with an A and B. So we'll say for A, B, and S. What do I know is in there? I want to show A plus B is in S. How do I do that with my subtraction thing? What's A plus B going to be equal to? How am I going to? Yeah, well,
We know negative A is an S, so we do B minus negative A.
B minus negative A. Yes, or we could do A minus negative B, right? Yes, so exactly. Yep. So by the previous part, we know that negative B is an S. That's the exact right idea. Yeah. So A minus negative B is an S. But A minus negative B is equal to A plus B. Thus A plus B is an S. Yeah, very good. Okay, so what we've shown is that instead of checking these 4 conditions, we could check 2 conditions instead. And many of you all realize that and use that in your homework, which is fine. Okay. Yeah, this is just because I kind of we were playing around and I wasn't proving theorems as fast as I should have been proving them. Okay. At least y'all are reading the textbook, so that's a good thing. Okay. So that was the end of chapter 3. Unless you have any questions on the homework that's due tomorrow is the last one from chapter 3. Any questions on that? I don't know if you've looked at it yet. Maybe you get one assignment at a time. Yeah, the 2 homeworks a week it's a lot, but I mean, it's like I kind of go back and forth between, am I giving you enough feedback and are you doing enough problems? And like, you kind of have to do problems to get a feel for what's happening. So I don't know. Anyway, we'll see what y'all have to say on the teaching evaluations. I have a fix again, don't worry. Yeah, oh, and I need to do those at some point. I just got them in my mailbox the other day. So we'll do those sometime. Okay, so let's talk about polynomial rings. So say I had something like this. So this is the notation. So if I had Z adjoin X, that is a polynomial ring. And so that would consist of polynomials with integer coefficients. Okay, is what that would be. Okay, so let's talk just a little bit about polynomials and kind of your experience with them. So what are some properties that we know about polynomials? In other words, what are the properties that we've done regarding rings do you think are going to hold true in polynomials? And we'll see if we can prove some of them. So let's just kind of think about what kinds of things would need to be true. Well, maybe even let's take a step back further. What does addition and multiplication, what addition and multiplication are we even talking about here? We've done a little bit with these, but what does addition look like in a polynomial? Or give me a polynomial with integer coefficients. Come on, it's going to have powers of x and integers. Okay, Jake, give me a polynomial.
3x squared
3x squared
plus 7x minus 2.
Perfect. Okay, someone give me another, so we'll call this after that. Okay, and then, let's see, Austin, give me another one.
5x squared.
Give me a different,
Oh, okay, you want
Something
5x cubed plus 2x squared minus 3x plus 1.
okay, perfect. Okay, so those are both elements of Z adjoint X, right? Because they are polynomials and they have integer coefficients. So what might we mean if we said, what does this mean? F of X plus G of X. What does that mean?
Summing those two polynomials together and combining them terms.
Yeah, that's right. So we're gonna sum this together and combine like terms. And so, yeah, so if we sum this together, so I'll have 3x squared plus 7x minus 2 plus 5x cubed plus 2x squared plus minus 3x plus 1. And so then we can combine like terms. So I'll get 5x cubed and x squared, so I have 5. Yeah, so that's what we would mean for addition. What do you think multiplication would look like? Yeah, I'm gonna, yeah, so essentially, I want to point out what we're doing here. Because a lot of times students would say, oh, we're gonna FOIL it out or whatever. Which is, that's fine, but really we're using the distributive property a whole bunch of times, right? It's kind of what we're doing. And so it's a mnemonic for multiplying two binomials, but it doesn't, that's the thing that where FOIL kind of breaks down to students. That's why I try not to use it, because it doesn't transfer, for larger polynomials or different. Okay. That's one of my little soapboxes. If you work at the MLSC, you hear these kinds of things from me all the time. I'm always like, oh, okay, so what are we doing? We're gonna distribute this guy across that, right? And so, what's it? Oh, yeah, gosh, okay. Peyton, hey Peyton, I'm sorry. Oh, Brittany, help me remember about you. Okay, so, yes, and that might. Okay, so what I'm doing is I'm going to distribute this guy, and it's not even better. Okay, and so I'm going to multiply that by that, and that by that, and that by that, and that by that, and then I'm going to distribute each of those guys into the other one, right? And so we're doing all of this distributing all at once. So the way that I'm going to do that distributing all at once is I'm going to do 3x squared times that, and then 3x squared times that, and then 3x squared times that, and then 3x squared times that, and so and go like that. Okay. So one thing we might notice here is that we're in the ring Z adjoin X, and Z is a commutative ring, right? So we're going to be able to move things around and gather like terms and things like that, but we need to kind of be aware that if we're in a non-commutative ring, things might work out slightly differently. Okay, one of the things that we're going to see for polynomial rings is that the coefficients are always going to be able to commute with the X, but the coefficients might not be able to commute with each other. Okay, so we'll have to be a little bit careful sometimes in non-commutative rings. Yeah.
Where is X coming from? Is it a real?
That's a really great question. I'm gonna let that question hang for a minute. Yeah, but actually, let me talk about it. So when we think about what X is, like if X is an element of Z, then why are we even talking about this, right? Because if we're multiplying X by other elements of Z, it should just get absorbed into the coefficients, right? And so it only really makes sense if we're allowing X to take on values that are not the same as the coefficients. But then what does it mean to say R adjoin X, right? could X be like outside of that ring? So I think these are really good questions. But yeah, so I think the idea is that there's some overarching ring that X is inside of, right? And then the coefficients are like a ring inside of that ring. Okay, so So in this case, you might think of X being a real number. Right? So, and in R adjoin X, maybe we think of X could be a complex number. Could be different. So it could be, I mean, but real numbers are a subset of complex numbers, so it could be real also. Yeah. Okay, so gosh, I don't really want to multiply this all out, but anyway, we can get started and then I can be like, then I'm gonna fudge the rest. Okay, that sound good? So I'm gonna get 15x to the 5th plus 6x to the 4th minus 9x to the 3rd plus 3x squared. So I multiply the 3x squared by each of those, and then I can do the 7x plus 5 times 7, what's that, 35? I'm really bad at multiplying. X to the 4th plus 14x cubed minus 21x squared plus 7x. And then I need to, now I'm going now, I'm just gonna do it all. I just did x cubed minus 4x squared plus 6x minus 2. Okay, so we multiply that all out and then we can gather like terms and so on. Okay, so that's what multiplication is gonna look like there. Okay, so this kind of like is the same as our experience before. But what if we had the ring Z mod 8 adjoin X? What happened in that room?
The coefficients would have to be mod 8.
The coefficients would have to be mod 8, right? The coefficients would have to be mod 8. So, oh man, I should have picked one smaller. Let's do mod something less than 5. Let's do mod 4. Z mod 4 adjoin X. Let's do Z mod 4 adjoin X. And so in Z mod 4 adjoin X, this thing, F plus G, would be equal to what in Z mod 4 adjoin X? Well, I just take those coefficients mod 4, right? So what we have? X cubed plus x squared, that would be 0 minus 1. And I could write that minus 1 as plus 3 if I wanted to in Z mod 4, right? If I wanted to write them all as positive numbers. So, so you can even think about what happens if your coefficients are a finite ring, right? And so there's some on your homework for Tuesday where you're doing some computations in the Z mod n adjoin X rings. Okay. So, all right, so we've got some plus and times. What about 1 and 0 in the Z adjoin X? What would the one element be? What kind of thing would it be? It would be a polynomial, right? A polynomial. And when you multiply it by another polynomial, it just stays the same. So what would that be?
Just 1, right?
It would just be 1, yeah. And so 1 we would say is a constant polynomial. So we think about 1 as or a polynomial. It's a constant polynomial. Yeah. So the 1 in Z, so the 1, well, should I write R? 1R is the constant polynomial 1, right? With no x's. And what would be the 0? It's just 0. Yeah, it's just going to be the constant polynomial 0. We talked about this a long time ago. Do you remember talking about this before? Maybe at the very beginning, I was talking about rings. Yeah, so the 1 is actually just going to be 1, and the 0 is just going to be 0 in that ring. Okay. All right. So what if we had? So do you think Z adjoin X is going to be? Is it going to be an integral domain or a field or anything like that? Is it going to have units? What do units and zero divisors look like in Z adjoin X? Okay, so let's think about this. Say that I have a zero divisor. then that would be some polynomial multiplied by another polynomial equals 0. So we're in Z adjoin X. If we have a polynomial multiplied by another polynomial equals 0, what does your experience with polynomials tell you?
It has to be, one of them has to be
One of them
0.
has to be 0, right? Yeah, and so we use that zero product property with polynomials all the time. You've used it a lot. But the reason is why? Because Z itself is an integral domain, right? And so if you multiply two things together and get 0, you know, if that happened in Z, it would I'm sorry, I'm kind of so the reason for this is that Z itself is an integral domain. What if I were in Z mod 4 adjoin X? Could I come up with two polynomials in Z mod 4 adjoin X that are 0 divisors? What would be an example of 0 divisors in Z mod 4 adjoin X?
2 and 2.
2 and 2, yeah. So even if I dealt with constant polynomials, I know that I could do 2 times 2 equals 0 in Z mod 4, right? So it's going to have 0 divisors in there. So when I think about 0 divisors, I really am looking at the ring that that makes up the coefficients. So can you come up with a non-constant? Can we come up with a non-constant 0 divisor in Z mod 4 adjoin X?
You'd like 2x and 2x.
Okay, so 2x times 2x, that's fine, David. So that gives us 4x squared, which is 0. Right? Yeah,
Could we have like 2x minus 2 and 2x plus 2?
let's see. Yeah, and so that's gonna give us what, 4x squared minus 4, which is 0. Yeah, good. So in a ring that has 0 divisors, if we do that ring adjoin X, we're gonna have 0 divisors. So what about units? Can we have units in Z adjoin X? If I have a polynomial times another polynomial equals 1, are there polynomials? You think our units would be in Z adjoin X?
I think that was like, I can't think of anything that would be in Z. So I can think of like 1 over whatever you have, and that would give you what you want. That's what I'm thinking about.
Yeah, that's not a polynomial anymore. Well, I mean, depending on what you're talking about. So are there any units in Z adjoin X? Are there units in Z? Zach's shaking his head yes. What are the units in Z? 1 and minus 1.
No, it's still working.
And so those would still work. They'd be constant polynomials in Z adjoin X. Yeah. So the units in Z adjoin X are plus or minus 1. Plus or minus 1 are units. Can we have any non-constant units
No.
in Z adjoin X?
I mean,
I think there would have to be something like a polynomial, like we had something that looked like, 2x plus 1, right? Can we multiply something by that and get 1? We need that x to go away somehow, right? And so the only way that would work is if we had it on the bottom, and so we ended up with these rational functions, which are not inside of our ring. So that was kind of a loosey-goosey proof, not really a proof, but
Counter example.
yeah, maybe a little counterexample that the only units are going to end up being plus or minus 1 in Z adjoin X. We're going to prove all this stuff a little bit we're just kind of talking today. So, what about in ZMod 4 join X? What would be the units here? Three, and yeah, well, so let's see, 3 times 3 equals one, right? 3 times 3 is 9, which is 1. And any other units? 1 is always a unit, so 3 and 1. So 3 and 1 are units. Could we have non-constant units?
Other than like 3x and 3x.
What if we had 3x times 3x, what does that give me? That gives me 1x squared. No, just not 1.
Yeah, you still have to get rid of the X.
We still have to get rid of the x, yeah. So could we do it so that like, okay, let's just play around with the linear one. What if we had like ax plus b multiplied by another linear one, cx plus b. And I want that to equal 1, right? So what has to happen? So I need ax times cx, I need acx squared plus ax times d, so I'm gonna have ad plus bcx plus bd plus 1. Okay, so what needs to happen? Well, I need this to be equal to 1. I need this to be equal to what?
Then
0 mod 4, right? And I need this to be equal to 0 mod 4. Okay, is this gonna be possible?
if you had like, if C and A were both 2, that would get rid of the first term. And then you could say B is +1, D is -1, which would make that additive inverses and it would cancel.
Okay, so we did,
But then we would end up with a -1.
yeah. What if C was -2 and A was +2? Did that work? William, did you have an idea?
I was just gonna say, like, if we modify the example with 2x minus 2, that was 2x minus 3, and 2x plus 3.
Oh. 2x minus 3 and 2x plus
No,
3. Oh, it would? Oh, yeah, because you get a -9. Yeah. It feels like something might work. Yeah. What do you think?
A and C are 2 and B and D are 1 at work.
Okay, let's see. If A and C are 2, so we'll have 2 times 2 x squared plus 2 times 1 plus 2 times 1 x plus 1 times 1. So that gives me 0, 0, 1.
Yeah. I didn't think about that.
Yeah, so in a ring like that, the mod 4 doing x, we can have non-constant units, right? So, so the additive inverse of, so what do we end up with? 2x plus 1 multiplied by 2x plus 1 equaled 1, right? And see my 4 doing it? Yeah. Okay. So, yeah, so let's think about what else I was gonna talk about. What are some terms that we might need to define? Do you have any polynomial terms floating around in your brain from high school that we might need to define here? Well, so we're not going to define composition yet because we're just going to use plus and minus for the ring. But yes, that would be one that we would need to define for. Yeah, I don't know if we're going to use composition for all in chapter 4, actually. Let's see. We were going to kind of focus in on like factors and divisibility of polynomials and things like that. And I don't know that we're even gonna go into composition. But yes, that's definitely something that's related to functions for sure. What about the degree of a polynomial?
Hmm.
So what's your understanding of the degree of a polynomial?
The highest exponent.
The highest, yeah, the highest power of x. Yeah, so the degree, and then the leading coefficient, right, would be the coefficient in front of the highest power of x. And then a constant polynomial we've kind of talked about, right? That would just be the constant part of that. Yeah, so we can kind of think about some of those things. So I think on that note, I'm gonna start writing down some theorems and proofs and definitions and stuff, okay? We kind of feel like you have your bearings a little bit for what we're talking about with these polynomials. And you may have never thought about, I think this one might be the most novel kind of thing, is to think about some z mod n adjoin x and what can happen there, because some different things happen there than in z adjoin x. And even we could talk about, you didn't really talk about this, but what about q adjoin x? And we can talk about r adjoin x. Right. So any of the rings that we have done up to this point, we can do that ring adjoin x and get a polynomial ring over that ring. Okay. All right, so let me define a polynomial ring. Oh, I should bring Peyton over here. So theorem 4.1 is kind of like the definition of a polynomial ring. It's going to be like, here, this thing is a ring and here are its properties. So if R is a ring, then there exists a ring T containing an element X that is not an R. Now this gets to William's question, right? What is X? Where does it live? Right? So this X can live in some, so we have this ring T and we have this ring R. These are my coefficients, right? And then X is out here. Okay. So so X can be some element that's in the larger ring that's containing the ring of coefficients. Okay. So we don't have to dwell on that too much, but anyway, that's just a little bit of the setup. Okay, and have these properties. One, R is a subring of T. Secondly, AX equals XA for all A and R. So, and I write this up here, but I want to point out that that doesn't necessarily mean that R is commutative, right? All that's saying is that X commutes with the coefficients, right? But the coefficients don't necessarily commute with one another because R might not be commutative. Okay, so I'm just going to put a little note here. This does not mean that R, the ring of coefficients, is commutative. Then we have this set R of X, R adjoin X, of all elements of T of the form And here's the form A naught plus A1x. So notice here we have a finite, so it does terminate, so we're not going to be talking about power series here, right? So it is a finite polynomial. So if the polynomial has to have a leading term and a degree and things like that, a finite degree. So you have to have n is greater than or equal to 0 and ai and r. And I always like to say an is non-zero because otherwise, like, why do we even include that last one, you know? So that's not in the definition, but I'm gonna put it in here. An is non-zero. Okay. It is a subring of T that contains R. And it contains R in the sense that R is the ring of constant polynomials inside of that ring, okay? So the ring of constant polynomials would just be the constants. And so R is contained in this ring R adjoin X. Okay, so 4 says the representation of elements of R of X is unique. So in other words, you know, if I write a polynomial down, I can't write the same polynomial with different coefficients, right? So there's a unique representation of a polynomial. So the representation so in other words, if I have, this is kind of a lot of notation here. I'm gonna have like this A naught through AN, like this polynomial, and then I'll have the ones with B naught through BN. Like if they're equal to one another, then all the coefficients have to be equal to one another. Okay. So if for n less than or equal to m, A naught plus A1 x plus A2 x squared plus dot 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 plus A n x to the n. If that's equal to B naught plus B1 x plus B2 x squared plus dot 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 plus BM x to the m, then what are we going to have to say? Well, the AI equal to BI. Yeah, yes. Well, yes. So we'll say it this way. So I said, oh, whoops, I did it the other way. The book does M is bigger than N, but anyway, I can say, for 0 less than or equal to I less than or equal to M, and the, okay, so I made N bigger. The AJ equals 0 R for J greater than M. Yeah. So yeah, so you're just saying, I guess that then I need to not say this because you're allowing the coefficients to be 0. So if I had that there, you would have to say N equals M. But anyway, okay. So does that sort of make sense? In other words, I'm saying all the coefficients have to be equal if the polynomials are equal to one another. Now, let's talk about over here. What was the polynomial I had here? I erased it. Okay. So I think I had in Z mod 4 adjoin X, I had like X cubed plus X squared minus 1. And I was saying that that was equal to X cubed plus X squared plus 3 in Z mod 4 adjoin X. Why does that not contradict what I said over here? Yeah, because really these coefficients are congruence classes, right? And so -1 is actually equal to 3 in Z mod 4. Okay, so -1 equals 3 in Z mod 4. So so even though I can write it, I can choose a different representative of my congruence class, it still does equal congruence class. Does that make sense? Yeah, Jake.
This may be a dumb question, but
There
like
is a
Z mod 4x,
Can you still have like x to the 5th power?
No, that's a really good question. Yes, you can.
Okay.
Uh-huh. And so, so I think your question boils down to, do the powers have to be elements of the ring of coefficients, right? And the answer to that is no. Yeah, so the powers are just gonna be regular old integers, yes.
Okay, I think I might have just, so you said the powers are integers. I was about to ask, can the powers be like rational numbers? But
No, okay, so the powers are natural numbers. Let me say that, the powers have to be positive integers, yeah. Yeah, no, that's a great question. Yeah, and the textbook actually goes through all of those little things, you know, so if you read in the textbook, you'll kind of see a lot of those questions that you're asking are addressed in the textbook, so. Okay. I have one more part of this one. So the fifth one says that A naught plus A1x plus A2x squared plus all that plus A n x to the n equals 0 r. If and only if what's true? What has to be true to make this work? Well, yeah, yeah, let's just say, so maybe, but I think we're not treating x as a number here. So it's only true if all of these coefficients are 0, right? So if and only if the aj's equals 0 r for all 0 less than or equal to j less than or equal to n. So if all of those coefficients are 0 is the only way you can get 0 in the ring. Okay. So other questions about polynomial rings that are coming up? So we're going to talk a little bit more about on Friday about degrees of polynomials, and when you multiply polynomials together, what happens to the degrees and things like that. And we'll also talk a little bit about, you know, if we know properties about this coefficient ring, what carries over into the polynomial ring, you know? So those are the kind of some of the questions that we want to ask. We've been kind of floating around some of those. And then guess what we're gonna have? We're gonna have this division algorithm in polynomial rings, right? So it's like we're going full circle back to the division algorithm. So we'll do the division algorithm in f of x on Friday. So we have that to look forward to. All right, see you then.
So next week, are we doing like a reading on Wednesday?
Yeah, let's do a reading on Wednesday. We're gonna have time for it. So. On Wednesday, bring all your old homework from chapter 3, and we can go over problems and discuss some of these.
Is the next one going to be 2 days as well? or-
No, it's just gonna be one day.
Okay.
So we'll review on Wednesday, and then it has to be Friday. Awesome. And then we'll be done. And you want to do any homework or everything's good?
That's awesome.